All right, so we're going to be PNE. Josh, PNE. Ready? PNE. What is PNE? We have P with plus sign, lowercase n with a zero. Now, if I did just a lowercase zero without anything on it, that actually would be the variable for a number of moles. We don't want to do that. And then we have a lowercase e with a negative sign. That would be. Now, what do these things represent? Yes, ma'am. Protons, neutrons, and electrons. So what we need to know from these is, what is their charge? What is their mass? What is their location? And what are they responsible for? Okay, so let's start off. Protons. What is the charge of a proton, Theodora? Okay, can we go a little bit more precise than just positive? We need to be a little bit more precise than just positive. What do we say if we want to be a little bit more precise than just a positive? Yes, exactly. It's a plus one charge. Everybody understand that? What would be the mass of a proton? Now, when we're talking about the mass of a proton, we're talking about a unit that's so small that we can't really measure it in this room. We don't have any means of measuring the mass of an atom, okay, or much less the mass of a subatomic particle. Somebody much smarter and deader than I came up with this unit. This unit is called an atomic mass unit, and a proton is one atomic mass unit. Okay? The proton is one atomic mass unit. What is the location of a proton? Where do we find a proton in an atom? Josh? It's found inside the nucleus. You'd be surprised at how many people today have been saying nucleus. It's not, there's no U in between the C and the L. It's nucleus. Excellent. Now, this is a real important thing here. What is a proton responsible for in an atom? Now, it's a little tricky when I'm going to give you guys this project called the Design Your Own Periodic Table project. On one of the parts is going to say, what is the nuclear charge? There's only one charged particle inside the nucleus, and that is the proton. So when I'm asking for the nuclear charge, you would just take the number of protons in the nucleus, and that is your nuclear charge. So it is responsible for the nuclear charge. But that's not the most important thing that the proton is responsible for. What is the most important thing that a proton is responsible for in an atom? At this point, I need everybody to look at your periodic table. Find the proton, or find the hydrogen, and find the calcium. And tell me the difference between hydrogen and calcium. Give me all the differences you can find between hydrogen and calcium. Go ahead, Theodore. Atomic. What is the atomic number? It's the order, but where did they get that order from? What is the atomic number? Where does the atomic number equal to? Where do we get that order from? Go ahead. Well, atomic mass is the weighted average of all of the isotopes of the element, And that was what Mendeleev arranged his original periodic table by order of increasing atomic mass, right? And we often say we no longer arrange our modern periodic table is no longer arranged by order of increasing atomic mass. Now it's arranged by order of increasing atomic number. So what exactly is the atomic number equal to? Go ahead. It's exactly that. The number of protons is the atomic number. So it's kind of important that we note that if I'm looking at two atoms, if they have a different number of protons, they're not the same thing. I cannot have two atoms of the same element that have different number of protons. It's not possible. Does that make sense to everybody? So what is it that the proton is the most responsible for? It provides the identity of the element. We're all riding the same roller coaster? Outstanding. All right, we're going to skip neutrons for a second here because we're going to come back to that. There's something special about the neutron that I want to talk about in a little bit. So let's talk about the electron. What would be the charge of an electron? Negative what? We got to be precise. -1. Outstanding. Okay, what is the mass of an electron? This is surprising to a lot of people. It's orbiting outside of the nucleus. Think about the planets in comparison to the sun. Are the planets even close to the size of the sun? No, they're a lot smaller, aren't they? If it's orbiting around something, it can't be nearly as big as what it's orbiting around. The reality is, if this is 1 AMU, for it to go around it, it cannot have very much mass at all. In reality, it is virtually zero mass at all. So the mass of an electron is virtually 0 AMU. Where would the electron be located at? We just said it's rotating around it, right? So we would call that outside of the nucleus. Now, what is an electron responsible for? I'm going to argue that an electron is responsible for half of what we study in chemistry. Are you guys aware of what the definition of chemistry is? Chemistry is the study of matter and the changes it undergoes. What's half of that? We've talked about matter, right? What's half of chemistry then? The changes. Half of what we're going to be studying is changes. Half of it is responsible by these electrons. How is an electron responsible for half of chemistry? Well, electrons are responsible for forming ions. If the amount of energy is different enough between atoms to yank electrons away from each other, they form ions. If it's not, then they will share electrons, called shared pairs. So this would be an ionic bond. And this is called a covalent bond. So all of this gives us reactivity. All reactions occur because of electrons. Does that make sense, everybody? So at the end of the year, we're going to be doing this thing called stars. It's a whole unit called stars. As you can tell, Beth, the TA, does not like this unit at all. But in the stars, we do a thing called nuclear decay. During nuclear decay, we might talk about a neutrino slamming into the nucleus of a substance. And when it does, it will slam into a neutron. And if that neutrino slams into a neutron, it might cause an electron to split off of the neutron, leaving behind it leaves behind the proton. That electron that slews off is essentially what is known as a particle. Does that make sense, everybody? It's a 0/-1 particle. Okay, that type of particle is a nuclear decay, but it forces a neutron to become a proton. How? It shoves off an electron. So what does that tell you that that neutron is made of? It is a proton and an electron fused together. A neutron is a proton and an electron fused together. So if a neutron is a proton and an electron fused together, what is the charge of a neutron going to be? It's going to be 0. What is the mass of a neutron going to be if it's a proton plus an electron fused together? What's 1 plus virtually 0? It's going to be 1 AMU. Where are the neutrons located at? They're inside the nucleus. Okay, what are the neutrons responsible for? Do they have a charge? No, so they can't form an ion. So they're not going to form any reactivity, right? Do they have a mass? So they do affect the mass, right? That's kind of important. Do we know of anything that can be affected or that is changes mass? Anybody ever heard of something that is different based only by mass? Anybody ever heard of a term of a substance that two atoms of something that just have a different mass? It's an isotope. Excellent. So when I put the emphasis on the wrong syllable, I like to call these isotopes, just so I can mess with people. I do like to do that. All right, now, anytime I have these, we're going to talk about these in just a second. Anytime I have these, it's important to note that there are many, many variables that involve isotopes. But when they become much larger, it affects the stability of the atom. So when I have these smaller elements like carbon, isotopes really don't affect the stability as much. There are some cases where there is an effect, such as carbon had some effect, but it's not as unstable as some of the later elements. Okay? Later on in life, when I look at these larger elements, the larger the ratio is between the neutrons and the protons, the more likely that the element will become radioactive. Reason being, as far as we know, that there's so much mass that the separation between the protons causes them to be instable. I'm probably slaughtering the pronunciation of that. Unstable, however. I'm putting the emphasis on the wrong syllable. It's a development problem of mine. I don't know. I have a problem with being able to concentrate. All right, let us talk about isotopes. What exactly is an isotope? An isotope is when you have two atoms of the same element with different masses. Okay? Two atoms of the same element with different masses. What's the same? What has to be the same? Protons. Can't be different. I have to have the same number of protons. Otherwise, it's a different atom. Does it have to have the same number of electrons? No, I can have charged particles and they can still be isotopes. I can have ions of isotopes, but I have to have the same number of protons. Have to. Okay? What is it that has to be different in order for them to be isotopes? The mass. And what changes to make mass different? What's a particle that changes to give us different? Go ahead. The neutrons. Neutrons change to give us isotopes. The electrons change to give us ions. Protons provide us the identity. I cannot change protons ever. Okay? So, when I'm talking about isotopes, I need to know how I'm going to define my isotopes. I define isotopes by the mass number. Mass number is not what you find on the periodic table. What you find on the periodic table is known as the atomic mass. That is the average mass, it's the average weighted mass of all of the isotopes based on their percent abundance. Okay? We're not talking about that. There are some people who give you a worksheet and they're going to say, take the atomic mass and take round it to a whole number and use that. I personally don't like to do that because you could do that and there might not even be an isotope with that number. I prefer to give you an actual mass number. How do I get a mass number? Mass number is equal to the protons plus the neutrons. That's how you get a mass number. Okay? Mass number is equal to protons plus neutrons. Keep that in your mind because you're going to rearrange that at times. Sometimes you're going to use this equation to find the number of protons. Sometimes you're going to use it to find the number of neutrons. Sometimes you're going to use it to find the mass number. But keep that in your mind. You need to know that. Next thing, hyphen notation. Very simple. If I have an isotope, I'm going to take the name of the element, hyphen, then I put the mass number. Simple example. Carbon has 3 isotopes. 2 natural forming, 1 unnatural forming, came about when some radiation was released. It absorbed it, created this isotope. Now anything that is alive eats it. When it dies, it starts going through half-lives, and we can tell how long something has been dead by measuring the half-lives of this carbon-14. That's how we know how long something's been dead, by how much carbon-14 is left in the system. But the hyphen notation for the 3 isotopes of carbon would be carbon 12, carbon 13, and carbon 14. Everybody cool with this? We have one more thing before we go into ions, and that is nuclear symbols. So we're going to take carbon again. We're going to put the mass number in the upper left, 13 on the upper left. The bottom left, we put the atomic number or number of protons. If this were to have a charge, we would put it over here in the top right. I'm not going to put one on there because I haven't talked about ions yet. We're going to do that next. But I could put a charge there. This is called a nuclear symbol. There are some worksheets that came from Central where they call this an isotope symbol because Central wants to try to change the names of things. I don't know why. Okay? Everybody got all this? Again, I'm going to put this up on my YouTube channel so you guys can come back and check it later if you need it. All right. Last thing we need to talk about, ions. Very important. Atoms gain or lose electrons. Notice, I am not saying anything about protons. We're not gaining or losing protons. It has nothing to do with neutrons. Nothing to do with neutrons. Everybody with me on this? So, unequal protons and electrons results in a charge. Unequal protons and electrons, it results in a charge. Okay. If protons is greater than the electrons, charge is positive. That means it lost electrons and is called a cation. How do I know that this is called a cation? A positive ion is called a cation because, everybody look over here. I need everybody's eyes right on me right here. You looking? Because cations are positive. Everybody saw that, right? So what are cations? Positive. I need to see it. Everybody come back with me. Cations are positive. Everybody got that, right? If you are so afraid to say cations are positive, you can go the wussy way and say there's a plus sign in the word. But I prefer cations are positive. Okay? Yes. All right. If the protons are less than electrons, then the charge is negative. That means we gained electrons and is called an anion. Now, I have no idea why this one seems so hard for people to get a way to understand this. This one jumped out at me immediately when I first heard it. Why is it that you know that an anion is the negative ion? A negative ion. It's pretty easy to me. Guys, that's what I need you to know for today. Your homework is page 6 in the pink packet. Let's get to work on that. Have a great one.